Department of Electrical and Computer Engineering and the Division of Biomedical Engineering, University of Saskatchewan, Canada. He received his PhD from the University of Rhode Island, USA, in 2002. His areas of research interest include computer architecture, efficient hardware implementation of compute-intensive applications, deep learning processor architecture, and biomedical engineering. He is an IEEE Circuits and Systems Society Distinguished Lecturer, a senior member of IEEE Circuits and Systems Society, and an associate editor of IEEE TVLSI, IEEE TCAS, IEEE Access, and IET Computers and Digital Techniques. He's an active member of IEEE CAS Technical Committee, IEEE Domain-Specific Accelerators Standards Committee, and IEEE Emerging Processor Systems Standards Committee. He was an associate editor for IEEE TCAS. Please welcome Dr. Seok-Bum Ko.
Good morning, everyone. First of all, I'm very excited to share some of my current research with you today. And I have to sort of apologize that I can't speak Spanish. So sorry about that. But, again, English is not my mother tongue. I'm originally from South Korea. I left South Korea in 1998. Since 2002, I live in Saskatchewan, Canada. So today's topic is efficient deep learning computation and its application. So we are enjoying the power of AI, deep learning these days from many, many aspects. But behind the deep learning, there are tons of computations going on inside. So my topic today is to optimize the computation, and using those techniques, can we really apply to the different type of applications, right? Because we are engineer and we love to contribute to the society, and we would love to see the real impact to the society and community. So I did a little bit of homework last night to provide a rough idea how Saskatchewan look like, at least here. This is Saskatchewan, and I'm from Saskatoon. So in terms of size, you can take a look at the size of the province of Azuay, sorry for my poor pronunciation, and Cuenca, compared to the Saskatchewan, and the country versus country, Ecuador and Canada. So hope that you can have a rough idea about the size and the population. A little bit of introduction of the University of Saskatchewan. It's one of top 15 research-intensive university in Canada. And we do have 2 Nobel Prize winners in physics and chemistry. There are a number of world-leading research centers on campus. Global Institute of Food Security and Water Security. And we do have only one national facility, Canadian light source on campus, because it's specialized in biomedical engineering. A lot of researchers all over the world, they visit to use the beamline of Canadian light source on campus. And the next one is the VIDO vaccine. So we do have a World Research Center on campus. So these are the number of things that we have on campus. If I narrow down to the computer engineering, we had Dr. Andrew Donald Booth, one of the computer pioneer. our time. So he was with us from 1961 to 1972. So he is the inventor of boost multiplier and many different type of magnetic storage. My research interest, sorry about that. My research interests include computer architecture, FPGA, and aging implementation of compute-intensive applications. So I'm going to focus on deep learning, FPGA-based accelerator, and it's some of the applications. These are the things that my current lab members are doing. If time permits, I try to cover as much as I can, but I don't think I can cover security and cryptography, which is one of the very hot topic and important topic these days. But I try to cover hardware design for deep learning here and some of the most representative deep learning applications today. So first of all, this is the simplest block diagram of my research work. My main focus is to optimize arithmetic units for efficient deep learning computations. There are many different ways, so this is the way that we are thinking that is important, and we can do that. So first of all, if you look at the left side, that's a general purpose computer arithmetic unit. So when I say general purpose, it's a CPU and GPU. So we have multiple precision FMA. FMA is the combination of multiplication and addition. And if you see the deep learning, in particular our students, basically the way how it works is that your input will be multiplied with weight, so you have multiplication, and this internal intermediate result will be added together, right? So that's the summation adder. And at the end, the bias will be added to this result, that you can get the output. So, no more than just the addition and multiplication continuously happening inside. So that's FMA, and multiple precision means in IEEE there's a standard. So all the computers that you have, tablet, it does have a 32-bit floating-point standard format, right? But 32-bit is not always sufficient. So my idea is can we implement the 64-bit in addition to 32-bit? And also 128-bit and 16-bit are also standardized in the format. So can we all integrate into a single chip? That's the basic idea. The second part is deep learning specific arithmetic units. I put NPU and TPU. MAC unit is more or less same as FMA, specialized in deep learning computation. And the same thing, the MPMAC. FlexMAC is in IEEE standard format. There is 3 components. Hope that you can remember: sign bit, exponent bit, and significant bit, right? So exponent bit, it's good to see some nods. Okay, so exponent bit is very, very important compared to the significant, because we are talking about 2 to the power of something, right? 2 to the power of 1, 2 to the power of 2. It makes a huge difference. However, the significant is 0 in binary, 0 point something. So it's very minimal. I don't think it will greatly impact to the total deep learning computation. So we try to use a exponent bit flexibly rather than having a fixed bit. We can try to use the best number of bits depending on the application. So that's the whole idea we named as FlexMAC. Approximation is another important means to optimize the computing operation inside the computer. Approximate computing, as you can imagine from the terminology, you can sacrifice the accuracy a little bit, but you can save a lot of power and area. So this is perfectly fit into the current IoT sensing era and also deep learning, because these are supposed to be embedded into your smartphone, for example. And to do so, your model must be small enough and compact enough to be implemented, correct? So that's approximate. So we do develop approximate floating point multiplication, and POSIT is the newest number representation format, which was introduced in 2017 by Gustafsson. So this one has its own way to calculate the number. However, I'm going to show the one graph that I hope that students in particular can remember what it means after my lecture. This is a very, very good tool for deep learning. So we try to develop the many POSIT-based arithmetic operator. Gustafsson is known as a Gustafsson's law. If you remember Amdahl's law, Gustafsson's law, that Gustafsson. One of my good friends who's in Singapore, he's a pure computer scientist. So when he developed this number representation format, he didn't understand the hardware characteristics, but simply just introduced the number format. So that's how we work together. The last one is a 3D memory architecture. I don't think I have enough time to cover that one. But if you see the in-memory computation, some of the simple operation can be done inside the memory rather than back and forth to the CPU, because it creates the memory bandwidth issue and bottleneck. Now, if I narrow down to the deep learning specific applications, there are 3 ways to improve the performance of deep learning accelerator. The first one is, if we can reduce the number of MAC operations to do certain functions, that's certainly ideal for us, right? So that's one of the ways. Second thing is, there are a number of processing elements. The problem is that we need to make sure that all the processing elements are hopefully and ideally equally busy. Not only single P is all the time busy, but the other 2, for example, among 3 are idle. This is not the best case scenario. So how can we enhance the utilization of processing elements? That's one of second topic. The last one is approximate DNN accelerator. So we can combine the approximate computing concept into the reconfigurable 8-bit booth multiplier. So this is booth, the computer pioneer that I introduced in previous slide. These are the applications that my labs are currently doing. The first one is intelligent transportation system. So we do license plate localization, license plate recognition, CVSA decal recognition, and hazmat placard recognition. I'm going to try what they are later on, so do not worry. Biomedical and veterinary sciences, you can see a lot of segmentation, classification, and detections going on inside. And we do use multiple imaging modalities, CT, MRI, and ultrasound, UTE, those type of things we are using into our research. So breast cancer, lung cancer, bone, rib, and dental caries, and so on. The third one is agriculture and the water resource protection. So we do use drones using RGB, multispectral, and hyperspectral images, and we try to predict the yield rate or plant detection and counting, plant phenotyping, and wheat or canola. These are the one of 2 major things in Saskatchewan. So we do try to predict the error rate. The last one is natural language processing. This one shows the difference between CPU and GPU, and as you can see, arithmetic logic unit components are dramatically changing from CPU to GPU. That's why GPU has a very fast computation time. Between GPU and TPU, it does have a specialized matrix multiplier unit, MMU. That's why it is specialized in deep learning computation. Okay, as I mentioned, we try to combine all together, half precision, single, double, and quadruple precision. Applications will be, deep learning or linear algebra calculations. So we try to make the entire function in parallel so that we can have a better throughput. The other beauty of this combination is let's say 128-bit. Okay, so 128-bit operation can be done in a given clock cycle. What if we have a 264-bit operations? Now, we do have a space to accommodate 264 operations, right? Which means if we can manipulate the data well, then 264-bit operations can be done at the same time, right? So throughput will be doubled. If you have a 32-bit operations, then 4 times 32-bit operations can be done. So 4 32-bit operations, which is the standard format, can be done in parallel. And if I go down, 8 parallel, half the precision FMA. So these are the entire idea. So we proved that, if you need more information, this one is available in IEEE transactions on computers. Second thing, I mentioned that we try to use this exponent bit flexibly, right, rather than having a fixed 8-bit. One of the current standard so-called P3109, the standard committee, we just made it as a standard draft. Now it is available to the public to get the recommendation and feedback. And if you look at the number of bits, as we are talking about 8-bit, so 16-bit in IEEE standard format is too much. So we are saying about the even less number of bits, 8-bit as a standard. So this one is specifically for machine learning. Now there are a number of evidence that why we could use a flexible exponent bit in particular applications. Now we did the same thing. Now if you look at the result, floating point 16-bit versus the proposed one, slightly worse. However, it does have a flexibility function, which is close to 32-bit, because if you go back, if you look at the exponent bit of floating point 32, it does have a 8-bit, right? And this one can this one can cover up to 8-bit, so more or less this B plus 16 can cover 32-bit operations. So that's the whole idea. Oops. Now if you look at this one, it's fair to compare the proposed with the floating point 32, not 16-bit. So now you can see the benefit of flexible floating point 16-bit compared to the 32-bit in worst case delay, area, and power. Okay? And we test this one into the real deep neural network applications. So we put the FlexMac as an IP. We develop our own test bench so that we compare with the real accuracy. So also this one is available in IEEE transactions on computers. This is the project format. I really wish some of you could catch the idea from today's lecture, and hopefully that you can use this one into your application, whatever you're working on. Look at this diagram. Green one shows the floating points right here, and magenta color shows the project. There are two things that we can see from this graph. Can anyone volunteer to say what two differences between two are? Let me provide one. If you look at the middle part, for a certain range, POSIT provides the better accuracy than floating point, correct? Okay, so that's the one advantage. What about the second advantage? If you see this part, floating point can't cover, right? POSIT can accommodate wider range than floating point. Because of those two advantages, this is a very, very good and powerful tool for your deep learning applications. All right? So simply speaking, if you can develop your deep learning model for, let's say, agriculture or biomedical or electrical power simulation, then you can compare with the floating point format and your POSIT format, right? Then your POSIT format will work much, much better. So we developed a number of POSIT-based arithmetic operations and multiplier, as I said, it's important. And we combine the approximate concept to the multiplier, and we specifically focused on the deep neural network computation, and we proved that. And these are all published in one of the major IEEE transactions. At the bottom, you can take a look at it. Now, this is approximate computing. I briefly mentioned that by sacrificing the accuracy a little bit, then we can get the power advantage and area advantage. So one example is that you can compare with the exact multiplier and the approximate version multiplier. It can save a lot of power. For example, 3 signals are required into the exact multiplier. Well, this one has only 2, and even further, we have only 1 signal is required to perform the multiplication. So now we can save the power up to 50%. So we published this one into Cancer Society flagship conference, IEEE ETCM, and also we extended the version of this work to the transactions on computers. Same thing for the divider. Softmax in your deep learning computation is quite important these days. So divider would be an important component. So what we did is in this part, the lower part, we replaced the exact cell with the approximate cell, and this is the approximate cell we developed. Then we could achieve the power consumption by up to 57%. Again, we did the same thing in 2019, and then we extend this one to IEEE transactions on computers. How do we accelerate deep neural networks? There are 3 different ways, but I'm going to focus on just the ASIC and FPGA today. There are a number of strengths and drawbacks among each other. So GPU-based and ASIC FPGA-based and in-memory computation-based. So first of all, these are the main general ideas. Once you brought the weight or input feature map, whatever from memory to your CPU, GPU, TPU, then we want to maximize the utilization of the data, right? Otherwise, data will be back and forth again to the memory, so that's not good. So by manipulating your data, once you brought it up to processing unit, then you want to maximize the utilization of the data. So that means local data views. And we can have some flexibility for mapping different layers. That's the second methodology. And we can try to support the approximate mode by accepting accuracy loss. And these are the things that we are doing in the lab. First of all, we reorder the computations positive to negative. So we combine this activation function to the last computational layer so that once the results reach the 0 or negative, then the remaining will be automatically negative because we manipulate the data, right? So we can stop at the point rather than completely finishing the entire function. So that's the whole idea of this. And we proved that, and we published into IEEE transactions on circuit systems too. If you look at this, these are all idle. So we try to solve these issues, and if you look at this one, they are all basically busy. The output is we needed 8 clock cycles, but just we need 4 clock cycles, right? So it's faster, and we can save the power, and also the computation is reduced by half. So this is the the comparison with the reference design, and this one is also published in Transactions on Computer-Aided Design of IC and Systems. These are common, right? So rather than doing multiple times, then we can extract those components into the smaller max size, and then they are all zeroed. So by doing that, we can reduce the computation delay, and also number of MAC operations reduced from 144 to 104. So that's the result, and we published this one, Transactions on Circuit and Systems one. We also touched the efficient spiking neural network as well. My expertise is purely digital design, but if someone is interested in analog design, this is a good a venue to work together, because by nature, spiking neural network can be nicely done by the analog design. All right. This is one of the most recent work, and we proposed a new encoding method based on power of 2. We named the PO2 into the boost multiplier, and we confirmed that this one shows the very, very good performance. So it is published in Transactions on Circuit and System 2 in 2023. And look at this table. This is a TensorFlow version. It needs 8-bit, and if they use a 4-bit, obviously look at the accuracy, 75 to 16, 96 to 9.979, basically useless. However, if you look at ours, proposed still use the 4-bit, which is the half of the TensorFlow version, but accuracy is pretty much competitive here and here for 2 different type of applications. This one, we try to reduce the number of the decoder rather than using typically n over 2, and we reduce it to n over 4. Okay? So that has been published in Transactions on Computers in 2024, this year. And this is some of the result. RISC-V, have you ever heard of RISC-V? Can you raise your hand? RISC-V is a royalty-free processor, which means you don't need to buy Intel processor, AMD processor. RISC-V is available to the public, so you can take the RISC-V and you put your own idea into the RISC-V. Think about Linux, right? Yeah, similar concept as Linux. Now we found out that we are unable to evaluate the varying forms of data flows and approximate multiplies impact. So we decided to make our own platform to integrate this RISC-V into TensorFlow. So we named the TensorFlow to RISC-V end-to-end framework. And this is what we vision to contribute to the technical society. And this is the work that we are doing. In RISC-V processor, we try to add a neural network inference engine. And this is some of the design features that we are thinking of. Transformer architecture is everywhere these days. And for example, one of the most popular natural language processing model, BERT model, it does have 12 layers, and many people found out that the 6 layers would be sufficient. The question is, how can we select 6 layers out of 12 layers? And we found there are some random methodologies, and we try to do first 100% of configuration trained for only 5% of the total time, and then we select half of them. In the second round, we use a 50% of configuration trained for now 5% to the 10%. So gradually, and you can reach up to the optimal the layers configuration. And we found out that this one works really well compared with a number of different benchmark circuits. So we published this one into our flagship conference, ISCAS, this year. All right, now I'm going to move to the actual applications. This is eye blood vessel extraction, because eye blood vessel provide a lot of important information: diabetes, Alzheimer, Parkinson's disease, right? But when you talk to the ophthalmologist, which is eye doctor, this is a very difficult job to extract the blood vessel from your eye. Compared to, let's say, 6 months ago, the patient's data and this data, it can tell like the blood vessel will be thick, right? Or thinner, or broken, things like that. So it can provide a lot of good information. So we automate this process using deep learning. Now, this is an interesting idea. If you are working on eye blood vessel research, and there are 2 major databases, which is a drive and stir database. Typically, people use one data set for training, validating, and testing, right? And we use the cross-used for our training and validation and testing. So for example, if we use our training on drive database, we test it into stir database so that we can provide the better robustness compared to the traditional one. This is a CT lung cancer detection algorithm. The way how we differently done at the time is this is done by the medical professionals, starting from medical students to the specialized specialist. The rightmost column shows the AI results. And the second round, we share the AI result with them, and then they had a chance to change their mind or update their result. And as you can see, it's clear that the AI can be a great supplemental tool, in particular for inexperienced health professionals. As you can see, it's clear, right? And the left side, the second round, the accuracy is much better than the first round. And also, we updated our model with different approaches, including like multi-pass feature extraction and multi-scale convolutional layer. And we proved that this one works better than state-of-the-art works. This one is about breast cancer. the ABUS, ultrasound is preferred by the patient because this is a non-radioactive material. However, radiologists, they don't like this one because it's because of the low resolution. So how can we solve this problem? Have you ever heard of the super resolution? Super resolution is to get the high resolution from low resolution data. There are many applications that you can use for this, using this super resolution. For example, think about the pediatric imaging, the younger children. Obviously, no one would like to see that radioactive materials to your kids or children. So that's the first place that you can do. Second application that I can think of is that in mining industry, they usually scan the surface by helicopter. It's very expensive. Now it can't come to the ground. Well, typically, when I talk to the mining industry people, they would love to get the 20-meter to 30-meter images, but definitely helicopter cannot run that range. Typically 100 is the closest from the surface. So that's the one of the good place to plug your super resolution. Anyways, we apply those techniques into the ABUS applications. So we proved that this one works better than any others. This is similar to CT and anterior mediastinal region, and we also proved that this one works well into the real clinical setup compared to the available one. Now, we develop our own layer, and we replace with the traditional layer in a number of different architecture, RASNet, 18 and 50 architecture in particular. And we proved that our version works much better in terms of accuracy. Also, in terms of the number of hyperparameters to implement, we've proved that this one dramatically reduced the number of hyperparameters. Now, we reduce the number of hyperparameters and we provide a better accuracy. That's super nice. How this one happened? Because we combined the unit architecture and the attention component into the unit architecture. So by combining those two, we were able to reduce the number of parameters and also improve the accuracy. AS, this is a sort of a bone disease. Typically, it takes 7 to 10 years to detect, even from a specialist point of view. It's a very tricky disease to figure out, and we developed a model using, modified Inception version 3, and we proved that this one works better than any other methodologies. So this one is published in Elsevier Computerized Medical Imaging and Graphics. Rib tracking and fraction. This is the one that I mentioned. We need to see the impact. Imagine the emergency room in the hospital. They are all panicked. Emergency doctor is very, very busy, right? The number one thing that they want to do, that patient has a broken rib one up. To do that, CT scanned images per patient, typically more than 300 images. And it's not easy to track each rib. We do have a 12 each. Now, due to the nature of the rib bone, it is overlapped. So it's very, very difficult to track that number 1, number 2, number 3, number 4, because eventually it's overlapped. So what we did is, let's skip all the details. Okay. Look at this one. This is the model that we developed. And you can see the red bounding box is predicted acute, which is broken. And the blue is broken, but it's now fixed, so which is old. And the green is regular. And if you look at the rectangular box, it says left or right, and the RIP number. This one is deployed to our university hospital, and we are running this one. It works very, very well. Obviously, it does have a limitation. For example, you have a collabo here, right? This one is sometimes mistakenly segmented as the first RIP, those type of things. But we're sure that we can remove those issues, and hopefully that we can deploy this one to the many university hospitals. This one is so-called gout. This is an interesting experiment as well. In particular, as you can see, this is a fairly new imaging modality, DECT, introduced in 2010. And at the time, people believed that, oh, this will change the world. But actually, it wasn't, because it provided too much false positive. And even if it says that gout patient, actually it's not, right? So we try to solve these issues and then combine the traditional computer vision techniques and with deep learning techniques. So we provide a number of papers into one of the prestigious radiologist journal, rheumatology, and a number of conferences papers. We got some post award as well. This one, also interesting project. When conducting surgery, surgeon's hand are typically occupied, right? There's no room to do any other things. Now, our research is to provide the best angle so that the surgeon can avoid poking the blood vessel, for example, right? Mistakenly, if surgeon poke the blood vessel, that's a huge, things to recover. So we try to provide the best angle to the surgeon, and we had a good result. Electronic nose, that can replace the dog, which is quite expensive at the airport. So what we did is we developed the LSTM model. Interestingly, compared to the traditional ML, strategies, KNN, SVM, and random forest, obviously CNN shows the better result. And look at the LSTM. Starting from 30 seconds, it shows the 100% result accuracy. But CNN, 3 minutes later, they started to catch it up. So we proved that LSTM works really, really well for this particular application. Now, I want to point out this work is done by one of my former students, Dr. Torres Tello. He's from Escola Politecnica Nacional, and he did his master in Milano, and he's currently working as an application engineer in Siemens. This one is to use a drone to predict the yield rate in canola crop. So we did a number of things to extract the best band from high spectral images, right? And we used a number of different techniques like pruning and shape. And then, well, this one is the same thing. One of the first authors, she's from Escola Superior Politecnica Ritora, and Julio Torres-Tello, the same one that I introduced. So we basically were able to implement this one into real resource constrained device like Raspberry Pi level. Because we found out that all the drones, because of the huge computation, they need to get on the ground and take out the SD card. And our idea is to use the real-time based prediction on the fly, right? So that's the whole idea. And yield prediction in aeroponics, also this one is done by Julio Prestello. And we try to combine multispectral images and hyperspectral images for different crops, and counting and segmenting a particular plants. That's quite common. Second one is license plate localization and recognition. So we use the SSD object detection network at the time, and we combine the research findings that we made to reduce the number of computations, right, into this one. And again, this one is done by Juan Yepes, my former PhD student, and he's from Escola Politécnica Nacional as well. So he's working in one of the largest ITS company in town right now. This is the one that we used, compared to the traditional one. Look at the method that we applied. This is the number of hyperparameters, so dramatically reduced. And we compare with the state-of-the-art works. Some of the works. And this is also hazard materials. Focus on top left corner. This is we deploy this one into real highway, and it's working fine. We're still collecting more data to fine-tune the model. If you look at the top left corner, it identifies the hazard materials correctly. Okay, so this is one of the work. And also, we use the neural network or architects to compare with other works. Super resolution I mentioned briefly, and this is a good tool for many different applications. This is the one from the 100-meter helicopter level. And we also use this deep learning techniques to detect the erosion in pipeline, because we do have lots of natural resources, and we use a pipeline quite a lot. Biomedical signal processing using EMG, we try to identify 6 different grasp types so that it can be used in robotic arms. And we developed a bidirectional LSTM-based model, and we compare with the state-of-the-art works, and we prove that our work works the best. Okay, this one is also done by one of my former PhD students from Ecuador. He's from ESPE, and he did his master's in University of Queensland, Australia. And now he just finished his PhD work and moved to University of British Columbia as a postdoctoral fellow. Teeth extraction, right? The whole idea is that dental panoramic X-ray is not popular in advanced country anymore. Bite wing, I don't know the situation in Ecuador. This panoramic X-ray is cheap, so it's popular to the unfortunate countries these days. So we use this panoramic X-ray images to provide the similar level with the current available material, like a bite wing, as I said. This is the one in advanced countries, and peripheral pico is also for that. But this one is getting to a similar level to test extraction, right? So that's the contribution. Also, using that extraction, we combine the segmentation, and later on, we try to detect the dental caries automatically. So this is the entire work that we've done. So let me skip this one. And also, we provide the COVID-19 diagnosis tool from chest X-ray directly. And we did a number of things into this version. Now, this is also interesting work I'm going to share. Probably this is the last work that I'm going to share today. Yeah. Automated carcass assessment system for swine welfare. Canada also provides a good amount of pork meat to the people. Now the problem is the welfare is not systematically monitored. So people usually, randomly stop by the pig places. There are a number of different places, right? And then see if they are doing all right or not. Now we are building the end-to-end system to monitor this one because veterinary scientists, they believe that the welfare is 100% related to the meat quality. For example, tail length. So we are trying to measure the tail length automatically using computer vision and deep learning techniques. It tells us that whether the nutrition level of the pig place is good or not. Because the nutrition is not good, then they try to bite each other, so the tail length will be shorter. Right? The shorter tail length means the nutrition level is not good. Something like that. So there are a number of different things that we can do, and we just made a patent, and many industry all over the world, they show the interest because there is none available for this end-to-end framework to monitor the entire pig stuffs. Oh, this is also done by one of my current PhD students, Francis Ferry. He's from Escuela Politécnica Nacional. So we are doing this one. This one might be a little bit cruel because the pig carcass, the pig body will be on the screen, but you can see what we are doing. See, right? We track the each pig, and also you can see, number of information that they want to see. Hernia, or right? So these are the things that we are currently doing. The current works that my lab is doing, we do have a lot of opportunities. So hopefully that I can see some of you to my lab in the near future. And this is the summary that I already shared with you with the block diagram. So I would like to acknowledge all the time and effort made by my students in the group, and also I want to appreciate the funding agency. Lastly, I would like to mention that my special thanks go to the ETCM organizing committee. That I had a great time to be here to understand what you think. So I have now a better idea how we can contribute to Ecuador. Once I get back, I'm excited to discuss all the potentials with my current PhD students. Okay, thank you so much.
Thank you very much, Professor. Do we have any questions for him? Okay, in this case, so we gave him a big applause again. And now please I invite Dr. Monica Huerta to give him a recognize a name of IEEE ETCM organizer. Thank you very much, Professor Seok-Bum Ko. Les recordamos a todos que el día de hoy, a las 3 de la tarde, tendremos la clausura del ETCM 2024, en donde estaremos reconociendo también a los mejores papers de cada track de este congreso. En este momento nos vamos a dirigir a las salas, las mismas en las que presentamos los papers, para las exposiciones de todas las investigaciones. Almorzamos y a las 3 en punto nos vemos aquí para la clausura. Que tengan buen día.